Welcome back to the class on a whole semiconductor drives. In this lecture, we are going to discuss about the speed torque characteristics of a DC motor. So whenever we are saying the DC motor, there are different types of DC motors are there. But in this lecture, we are going to discuss about the DC shunt motor and the series motor. The shunt motor speed torque characteristics same as the separately excited shunt motor also. DC motor. DC motor is the electrical machine which converts the DC electrical input to the mechanical output. So this is the circuit diagram for the DC motor. This is the field winding. This is the armature winding. For the armature winding, we are applying the DC voltage. Whenever we apply the DC voltage, the current is passing through the armature winding through the brushes and commutator. Whenever the current carrying conductor placed in the magnetic field, every conductor experiencing a force. So collectively, the torque is developed at the shaft of a armature. The armature will be rotating in a one direction. The direction in which it has to rotate, it is highly depending upon the direction of flux as well as it is depending upon the direction of the armature current. Now we are assuming that the armature will be rotating. When the armature is rotating, it is rotating in the field. There is a dynamically induced EMF in a armature. That voltage is nothing but a back EMF that is just opposite to the applied voltage. So why we are calling this voltage as a back EMF means because it is opposing the applied voltage. That's why we are calling it a back EMF. Now the expression for the back EMF is equal to EB equal to Zn pi by 60 into P by A. We know this expression. Now here, just we are modifying this equation because we want to find out what is the relation between the speed and the torque. So here each variable is defined. Z is nothing but a total number of conductors, N is nothing but a speed of a motor in RPM, pi is nothing but a flux per pole, P is nothing but a number of poles, A is nothing but a number of parallel paths. It is highly depending upon the whether it is wave winding or the lap winding. Now the equation 1, we have to multiply with the numerator and denominator with a 2 pi. We are getting this expression 2 pi by 2 pi into Zn pi by 60 into P by A. Now you separate the 2 pi and 60. 2 pi and 60 that we can write it as a omega because that is the angular speed of a motor in radians per second. So 2 pi n by 60, if we write the omega equal to 2 pi n by 60, the remaining constant Ke that we have taken is a Ke that is equal to 1 by 2 pi into Zp by A. This is also nothing but a motor constant. So because once the motor is designed, the number of conductors in a motor, the number of poles in a motor, number of parallel paths in a motor is constant. So that's why this is the constant for a given motor. So the EB we can write it as a EB equal to Ke into omega into pi. Nothing but the back EMF in a motor is directly proportional to the speed of a motor in radians per second and pi. This you have to take it as a equation 2. This is a general expression for any type of motor. That may be shunt motor, series motor, or the compound motor, whatever it is. The torque developed in a motor. Already you have seen that there is some amount of torque is developed at the axis of a shaft so that the armature will be rotating. Now, what is the formula to find that torque means? T equal to 1 by 2 pi into ZIA pi into P by A. Now we are defining the each variable. Z is nothing but total number of conductors, IA is nothing but armature current in amperes, pi is nothing but a flux per pole, P is nothing but a total number of poles, A is nothing but a number of parallel paths. It is also depending upon which type of winding, that is wave winding or the lap winding. Now here, now we are rewriting this equation T equal to Ke into Ia pi, where Ke already we defined this constant. This is a machine constant, nothing but Ke equal to Pz 2 pi A. This is the machine constant which is constant. So now the torque is equal to the equation 3, we can write it as a Ke into Ia into pi, because we can find the same constant in speed as well as the torque constant. In case of shunt and separately excited motor, the flux is constant. Once the flux is constant, the back EMF This is EB equal to KE into omega into pi. This pi is constant. So KE and pi also constant in case of shunt and separately excited motor. So we replace the KE into pi with a separate constant, that is K. So EB we can write it as a K into omega. Again, we have taken the torque equation T equal to KE into IA into pi. In case of shunt motor, the pi is constant. So KE into pi, again you have to take the same constant K. The torque developed in shunt motor, that is equal to K into IA. Now, from this expression, if you find the armature current equal to torque by this constant K, where K equal to KE into pi. Suppose if you apply the KVL in a DC motor, if you find the back EMF equal to applied voltage minus IA RA, because here we neglect the voltage drop across the brushes. We know the expression for the back EMF. Back EMF equal to K into W. This is fundamental equation. This is the voltage equation we are getting when you are applying the KVL to the motor. Now these two are equal. K into omega equal to V minus IRA. Now we wanted to find the speed because we want the relation between the speed and the torque. So omega equal to V by K minus, in place of IA, you substitute the equation 7. IA we can write it as T by K. So we are getting the T into RA by K. This is the final expression for the speed versus torque in a shunt motor, where the flux is constant. If you observe here, this is the applied voltage that is constant. If we make it, if this is a constant, this is the constant, K is also the constant, RA also constant, K is also constant. The only one parameter which is changing, that is the torque. At no load, the torque developed in the motor is 0. So this term becomes a 0. Now we are going to draw a plot between the speed and the torque of a shunt motor. Torque we have taken on the x-axis, speed we have taken on the y-axis, the speed in a radians per second. This dotted line is nothing but a no load speed, where the applied torque of the motor is 0. Goes on increasing the load from no load of a motor, the torque developed in the motor also will be increases, the speed of the motor will be decreases. This is the speed of a motor. So why this is decreasing means, because the torque is increasing, this term will be increases. It is simply subtracting this term, so the speed of the motor will be decreasing. Sometimes how much the speed is decreasing, it is not only depending upon the torque, it is also depending upon the armature resistance of a winding also. Now we are going to see the speed torque characteristics of a series motor. In case of series motor, again we have taken the same back EMF equation. EB equal to KE into omega pi SE. Pi SE is nothing but a series flux. This series flux is proper. This is the series mission. This is the armature winding. This is the series field winding. We apply the voltage. The current is passing through the field winding and the armature winding. Same current is passing. So this flux is proportional to the armature current. So series flux is proportional to the armature current up to the saturation of this speed. We always operate this mission in a linear region only. So the series flux is proportional to the IA. Now to remove this proportionality, you have to keep the one constant, that is pi SC equal to KF into IA. In place of pi SC, you substitute this one. The back EMF in a series motor EB equal to KE into KF into omega into IA. This is the constant. This is the mission constant. This is the field constant. The both we are replacing with a one more constant, that is K. So EB equal to K into omega into IA. Again, we know the relation for the EB. If you apply the KVL in this loop, we know the one more relation, that is EB equal to V minus IA into RA plus RSC. This is the fundamental expression. This is the voltage equation. Now we are equating these two. When you are equating these two and find the value of speed, because we want the speed. So we are getting the expression speed equal to V by K into IA minus RA plus RSC divided by K. Now here, this current we have to replace with a torque developed in a series motor. So to replace this current in terms of torque, we are going to take the torque developed in a series motor. The torque developed in a series motor, this is the fundamental equation. T equal to Ke into Ia pi SC. K is nothing but a motor constant. Now again pi SC is proportional to the Ia. To replace that one, we are keeping one more constant, that is Kf. Is in place of pi SC, if you substitute this one, we are getting the torque developed in series motor equal to Ke into Kf and Isk. We have taken one more constant, that is K. So from this relation, we are going to find out the Ia. If you find the Ia, armature current, Ia equal to root E by root K. We know the speed equation in series motor, that is omega equal to V by K into Ia minus Ra plus Rsc by K. So in place of Ia, you substitute this equation, you are getting the speed torque characteristics of a series motor, where omega equal to V by root K into T minus Ra plus Rsc by K. See, this is the constant, V also the constant. So here the variables are the speed as well as the torque developed in a series motor. If you draw a plot between the speed and the torque of a series motor, take the torque on x-axis, speed on the y-axis, it is representing the rectangular hyperbola. Torque is lesser, the speed of the motor will be higher, and the torque is higher, the speed of the motor will be lesser. Oh, before going to close this class, just we are going to summarize very briefly about this class. We have discussed about the speed torque characteristics of a shunt motor as well as a series motor. The speed torque characteristics of series motor is rectangular hyperbola, whereas in case of shunt motor and separately excited motor, as the torque on the motor is increases, the speed of the motor will be slowly decreases. So thank you very much. If you have any doubt, you can ask me directly, or you can ask me in the comment box of my YouTube channel, so that I am available to answer all your questions.